In this video, I'm going to talk about an alternative way to formulate the post office scheduling problem. In the video before, we used these different sets to distinguish who is working on what particular days. And so with this alternative, I am going to do a slight variation that is exactly equivalent for the post office scheduling problem. And so just to reiterate here, our decision variables are exactly the same. However, our parameters are different. We don't need days, so no days there. We don't need DI. And what we're doing is we're replacing it with a couple different parameters here. So first I'm going to introduce M and say that this is equal to the number of days. And so for our problem, M is equal to 7. Then instead of having these sets, what I'm going to do is I'm going to introduce a parameter Aij. And I'm going to say that Aij is equal to 1 if shift J works on day I, and this is for I equals 1 to M and J equals 1 to N. Okay, and so for our particular problem, just to reiterate here, if I have Aij, and that might not actually be big enough there, let's just make this slightly bigger here. So we have a matrix where if you break this down, we have I, which is a day. So you think you have days going down here, and you have shifts going, shifts going there. And so we're going to put a 1 if this shift works on this day. Or you can think you can go down by days here and go across and say, does this shift work on this particular day? And so I'm going to just fill in a couple values here, and then we'll interpret it. I'll actually just fill in this whole matrix. Okay, and so just reading this, this is day, the first day here, and this is our first shift. So we're saying shift 1 does work on the first day. However, shift 2 does not work on the first day, and shift 3 does not. So we can use this to know which shifts work on which particular days. Then we have, as we had before, we have our I as our staffing requirement. But now it doesn't go over this set of days. It just goes for days 1 to M. So staffing requirement for day I, we can't have a lonely subscript for I equal 1 to M, our number of days. Then when we put this all together here, we can have a model that looks similar, it's equivalent, but it's slightly different. So here we have our model. We're still minimizing, but now we're summing over our days, J equals 1 to M, our cost that we have as defined before, Cj multiplied by Xj. Subject to, now we have our staffing requirement. We must meet that staffing requirement, and this looks slightly different with our new parameter Aij. I'm still summing over my shifts did I say that I was summing over days here? I actually meant I'm summing over shifts, the cost of the shift multiplied by how many people are working that particular shift. So if I said days, I meant shifts. Here, again, I'm summing over my shifts, j equals 1 to m. And let me just, this should actually be n. So just to make sure, keep your m's and n's correct. Here, I'll leave it like that, so as a learning lesson here, this should be j equals 1 to n. N is our number of shifts, m is my number of days. So here, down here, this also is j equals 1 to n. Okay, I'm summing over my shifts. I'm multiplying aij by xj and saying that has to be greater than or equal to ri for all of my days. So days, I'm indexing by I, and this goes from I equals 1 to m. Then I have my non-negativity like we had before, xj greater or equal to 0 for j equals 1 to n. Our description is exactly the same. So this is just an equivalent way to represent the post office scheduling problem when we're using what's called these binary parameters, a 1 and a 0, rather than those different sets.